everyone. Thanks for joining today our Tidal Flat seminar series. My name is Nina Stark. I'm here at the University of Florida, an associate professor, and also the project lead for the research project that this Tidal seminar series is part of. This is an Office of Naval Research funded project called Littoral Mudflats and Shorelines, Soil, Sea, Ice, Air, and Benthic Life Interactions. The project aims to develop a fundamental and comprehensive understanding of the geomechanics of littoral mudflats and shorelines towards reliable prediction of geomorphodynamics, trafficability, and navigation from satellite images and geoacoustic surveying. The purpose of the seminar series is to get results of the project out, but also to foster collaboration and interaction with other researchers all over the world who work on muddy tidal flats. And so we're super excited to have Professor Bram from Prooijen here today. He got his PhD in turbulent flows in 2003, and after that he worked as an engineering consultant before he returned to TU Delft in 2008, where he started working on biogeomorphology of estuaries, and he's now heading the coastal engineering section and doing research on estuaries with a strong emphasis on field work. We are really excited to have you here, Bram, and with that, I hand it over to you.
Yeah, thank you very much. Thanks for joining. I will give a presentation on hydrodynamics on muddy tidal flats, and as you can see here, I hope everyone can hear me and see me, and also, or at least see the slides. Otherwise, let me know. A tidal flat in the Western Scheldt on top is the figure, and I think it is similar to many tidal flats in the world. Maybe good to mention that we in general also have a lot of dikes along these areas. So contrary to I think United States, we have quite high dikes, levees around the estuaries next to our tidal flats. The other picture is indicating that, well, I like doing field work, and many of us do in our group. And one of the key parts of doing field work is also having a bit of fun. And I think that this picture also shows that. Let's continue. Let me see if this works. Yeah. So the Netherlands. Do you see my whole screen, or do you also see the? Okay, because I do not see. Do it like this. Yeah. So in Europe, we are in the Netherlands over here. I added Florida over here, and what you can see here is that the Netherlands, we have quite some water, and a lot of the Netherlands is also below sea level. I will be talking a lot about the Eastern Scheldt and the Western Scheldt and the Wadden Sea. These are three areas that are important in our system, and where we also find all these intertidal flats. And I am Delft is over here approximately. I'm living a bit more to the east, and at the moment I'm close to the island of Texel. Maybe also good to indicate, this is approximately the distance between Miami and Orlando. So we're talking about the Netherlands is like 300 kilometers long. So these estuaries are not as gigantic as you can have in other areas. See another picture, because the Netherlands, we do a lot of engineering works in our estuarine systems to keep it livable, let's say. After the 1953 storm in the Netherlands, we built this Eastern Scheldt barrier, which is partly closing the estuary of the Eastern Scheldt. This is the Western Scheldt, the southern one. Yeah, so that's a bit a difficult thing. The northern one is the Eastern Scheldt, the southern one is the Western Scheldt. And this is the gateway to the port of Antwerp, and therefore you see a lot of shipping in this area, and also a lot of dredging over there. So there's a lot of dredging going on, which also, of course, also has an impact on the tidal flats. In the north, this is what we call the Afsluitdijk, is a long a dam closing of this lake from the Wadden Sea. So as you can see, we do quite a lot in the estuaries to make it in some way livable, but of course that also has impact on the natural values of these systems. Well, we of course expect quite some changes in sea level. This is the prediction for coming years. We are now here and we measured since 1900. These are predictions up till 1 meter. Well, if that's the case, then that will have quite some impact on our tidal flats and of course also on the Netherlands itself. There are predictions further than 2100, but this is already quite impactful. So how do the tidal flats look like in the Netherlands? I think that's also quite similar to what you are used to. However, most of our tidal flats are accessible from land, or at least a lot. So that is also helpful for doing field work. But of course, you see all kind of marshes, but also these tidal flats that are just extremely flat, but also all kind of other things. What's interesting in the Netherlands is as well that we have a lot of people walking on the tidal flats as a, let's say, recreation. So you can walk to the islands in the Wadden Sea, for example. And as indicated, we generally have quite some high dikes of a couple of meters high to protect the land behind the land behind. So for today, what I would like to do is I would like to try to give an answer to all these questions, but also already did the disclaimer that I will likely not have an answer to all these questions in sufficient detail. So, but let's have a look. Additionally, I would like to share some of my own experiences here. If you want to do field work in muddy tidal flats, then these might be helpful. And the first one would be avoid waders, but wear wetsuits. My first experience was above here. I was wearing waders, and that didn't work out. If you wear these wetsuits, these are pretty good, and since over a decade, I was never stuck again. And they are warm enough, also important in the Netherlands. Then we go to the Western Scheldt. By the way, if there are questions or other things, let me know. I only see my own screen, so in that sense, it's a bit less interactive. The Western Scheldt, we are in the south of the Netherlands over here, and we look at this estuarine system. And what I would like to do is first look at how does the tidal flow look like in these kind of systems. So we measured at all these locations. We measured flow velocities with these kind of instruments, aqueducts. These are ADCPs from Nortec, and they can give a flow profile for a couple of meters high. Well, if we look at this, then first have a look at the water levels, and what we see is a change in water level during spring tide, neap tide. These colors indicate the different locations, as we can see over here. So the red one is the upper tidal flat, and the green one is the lower tidal flat, and the black one is in the channel. So this is the height of the instrument. So what you can see is we have a tidal range between 3 and 5 meters, and we see quite a strong tidal asymmetry. especially during spring tide. So this is the spring tide period, and this is the neap tide period. If we look at the long shore velocities, we see a similar kind of thing. Of course, we see the spring tide and a neap tide. Velocity ranges between 0.5 and 1.5 meters per second, and we still see a strong tidal asymmetry, especially during spring tide, and we see this very high peaks during flood. If we look during the neap tide period, then the flow velocities are obviously much smaller. And what we also see is that if we go to the upper tidal flat, then we also see that the velocities decrease. So closer to the channel, we see higher velocities than higher up on the tidal flat. Well, we'd like to see if we can predict those, and if you use the Reynolds equations, then you can simplify these. And if we then only leave us with the friction term and the pressure gradient, and if we balance them, then we get something like the Chauzy equation, or let's say an equation where the flow velocity depends on the depth, the water level slope, and some kind of a friction coefficient. And interesting here is that if we assume that this water level slope is uniform over the full tidal flat, if that's the case, then we would have a Froude number that is kind of uniform over the tidal flat. And if we plot that, then we indeed see that, especially during during neap tide, that all the lines kind of collapse, indicating that the Froude number is similar at the same time. So that means that at all the different locations, we see that the Froude number is the same. So this is an indication that if we scale it with the water depth, and that's actually what we do. So if we scale the flow velocity with the square root of GD, then we get a pretty similar kind of pattern. So that means that the flow velocity is highly driven by the pressure gradient and the friction. Only during, let's say, these peaks, and especially also during just before wetting and drying, then we see quite some deviations. So of course, it's then difficult to determine this water level slope, and luckily we could measure that. We measured it based on our own measurements, but also based on two tidal stations that are 22 kilometers from each other. And if we do that, then we could determine the water level slope for both methods, and they are pretty similar. So based on that, we can simplify that. And based on that, we can calculate the flow velocity based on the water level slope. So going back to this equation, so if we know the water level slope here and we calibrate the friction coefficient, then we can determine the flow velocity for each water depth. And that's what we did here. And as you can see that especially these kind of plots are okay. This one as well. Here, of course, we see still some deviations during spring tide, the flood velocities. But overall, there's at least a reasonable agreement between the prediction based on a uniform water level slope and the measured flow velocities. So that means that the flow velocity is pretty friction driven. So what did we learn from this? Flow velocities can be pretty well estimated by balancing the pressure gradient and the friction. And secondly, if we assume a spatially uniform water level slope, then we can predict the water level, the flow velocity in longshore direction. Of course, things become more complicated if we add the impact of wind. But before, I think it's important to indicate another important aspect of doing field work. And I think that is arranging great food. And not only during, but also afterwards. I think that helped most of our field work to become a success, especially during the field work, but also afterwards, where we eat here some fish with Chinese colleagues. But let's continue on the impact of wind. So we already indicated this part of the equation. Adding wind leads to an additional term based on the wind speed, some kind of drag coefficient, and of course the relation between the density of the density of air over the density of water. As we just saw, we can describe the flow velocity due to tides based on the water level gradients. And if we implement that, we can come up with a new flow velocity that is influenced by tides and waves, so T and W, based on something that a velocity that you would expect from tide only, and an additional term based on the wind speed. Well, as you can see, this is a non-linear term. So if we implement that, so if we, for example, for 0, 0.2, 0.4 meter per second for the tidal contribution, and then if we have minus 15 meters per second or plus 15 meters per second of wind, we see that we get this line or this line. So how to read this kind of plot? Well, if we have a very small tidal flow, then you see that the flow velocity due to tides and wind is mainly caused by the impact of the wind, positive or in this case negative. If we have a very strong tidal flow, then we are in this part of the range, and we see that we are very close to the tide-only simulation, the prediction. In between, you see that there are deviations, and especially if the wind is against the tide, we see that for a long time, the wind is kind of winning from the tide. Until this point, where it is 0, we see that the flow velocity reduces to approximately 0, and for higher tidal flow velocity, we see that the tide is winning. So over this period, we see that actually the wind is winning it from the tide. So in that case, we would never have an ebb flow during flood, during the whole tide. In other words, the wind can reverse the tidal flow. And that's also what we measured. And now we are in the north, in the Wadden Sea. We did all kind of measurements during different wind speeds. So in this case, we had the situation on the left-hand side where we had no wind. In the middle, we had no wind from the northeast and wind from the southwest. And what you can see is that especially in the wind from the southwest, we see first of all the water levels here, and here the flow velocities. We see that the flow velocity is always in the same direction. That means that we have no ebb flow anymore. So this indicates that the flow velocity can be overtaken by the wind, and that's actually something that we did not really think of when we started it, because we thought, these are tidal flats. So tidal flats means that there's a strong impact of the tides. but apparently the impact of the wind is much stronger than we thought. And if we look at sediment transport, then it's even stronger. So what we see here is in blue is the sediment fluxes. So that's the flow velocity times the water depth times the sediment concentration. And if we can also accumulate that, and then you get the black line. So what we see is that the changes of the accumulated sediment flux are highly impacted by the wind direction. So we see strong steps positive upwards for wind from the southwest, while we see negative fluxes if the wind is coming from the northeast. So what we see here is that the net sediment flux is highly depending on, well, let's say these wind events. So then, after all, the net flux is more impacted by these wind events than the general or normal mild conditions where we have tides only. So that brings to the second conclusion. Wind can substantially change the flow speed and direction and even reverse the flow. And wind determines the net direction of sediment flux. And especially on tidal flats, that can be quite a lot. Then we go to the part on waves. But again, another advice I would give, if we did quite some field work, and these kind of sleds that you see here, you can pull them. These were super useful, and we also made some our own, and especially the ones where you can lean on a little bit. That really helps, because then you don't sink in that deep. And especially that's the case if the mud is somewhat less consolidated than on other parts. We go back to the Western Scheldt to show some of the results that we obtained here. And here I show some results from two frames that we had here, the two red triangles. And we had frames like these, and good to mention that we had these ADVs, Nortec vectors, and with these we can measure the flow velocity at quite high frequency, but also waves, because we measured at 8 Hertz. And we can also measure the bed level, so the distance between the sensor and the bed. And you can do that by measuring in burst mode. So it measures at the beginning and at the end of each burst. Well, if we then look at a cross section over here, then we had a measurement point over here, one of the frames. And if we then look at the change in bed level, then we see over this period, we see almost no change. However, if we look at the location F1, which is close to the mean low water line, we see that there's a sudden drop in bed level of about 20 centimeters and a recovery within a couple of days. So if we then look at what's happening, we see that the wave height was quite high over here. Well, relatively high, of course. It's tidal flats. We are not on sandy beaches. So relative high means above half a meter. And this resulted in this erosion. Well, interesting enough here is that at this moment we didn't have spring tide, but we were closer to neap tide. But what we see is that exactly during this period, we see that the water level is almost almost at low water, but because of some wind setup, it is a bit higher than the normal low water. Well, if we look in a bit more detail for this period, then we see that the wind speed is slightly higher than 20 meters per second. And if we look at the flow velocity, we see that we have quite high flow velocities during a period where the water depth is relatively small. And in combination with the wave height, that leads to quite high bed shear stresses. So as the bed shear stress is not only dependent on the wave height, but also on the water depth, we see that there's quite some impact over here. The concentration itself is actually not that high, but the combination of shallow water, high waves, and strong wind, that leads to both resuspension of sediment, but also the transport of sediment, and that led to the change in bed level. Because if we look at the other stations, for example, the deeper one, we don't see substantial flow velocities here. And as indicated already, the higher frame was not even flooded during this storm. So we especially see that at this location there's a high wind speed leading to both high waves and strong wind-driven flows. Another example, this is an example of numerical simulations. Here we are in the Eastern Scheldt, one of these shoals that we look at. And the Eastern Scheldt, in the Eastern Scheldt, a lot of the intertidal areas are eroding, mainly because of the storm surge barrier that is over here. I have later on some more plots on that. But the storm surge barrier is in normal conditions, it's open, only closed during storm conditions, of course, but it reduced the area here, the cross section, and therefore the tidal range decreased in the Eastern Scheldt, and that led to erosion of the tidal flats. So what did we do? Because that's the cool thing of numerical modeling. You can switch on and off different processes, and in this case, we did simulations with different processes, with waves, and of course tides, but also with and without wind, and also the effect of a storm surge, so an increase in water level. Well, if we look at the sediment transport, then we see this kind of pattern. So we see a lot of sediment transport over here and a bit less over here, mainly because of waves. But we do see some sediment transport in northeastern direction. So this is a simulation where all the processes are on. So that means waves and wind and also storm surge. If we exclude the waves, then we see that there's almost nothing happening. So it indicates that waves are an important forcing for sediment transport. If we switch off the wind, then we still see some effect here because of the waves. But in general, on the tidal flat itself, the transport is pretty small. So it is the case that sediment is steered up by the waves, but it's not transported by the wind-driven flow. Only if you look at the situation with no storm surge, then the impact is smaller. So what we see here is that this plot, the lower right one, is approximately equal to the upper left one. So the impact of the surge is much smaller. But the main message here is that waves are important for sediment transport, but we also need the wind-driven flow to transport the sediment. So it's not only steering it up, but also transporting it. Well, we can even explain that further. So what we did is we determined the full year of simulation, and we sorted all the different tides based on the wind speed. So on the left-hand side, we have the tides where the wind is not important. On the right-hand side, we have the tides where the wind is super important. So if the wind would have no impact at all, then we would get a straight line here, because this is the accumulated sediment, the percentage of sediment transport. And what you see here is that most of the lines, especially the purple one and the green one, they are more curved. And it approximately means, so if we are, for example, here on the green one, that 90%, or sorry, that only 10% of the tides, so the last 10%, results in 80% of the sediment transport. Or in other words, the first 90% of the tides only resulted in 20% of the sediment transport. So indicated again that the influence of waves and wind is quite important for tidal flats, as indicated also here. Then to the influence of the bed strength, possibly also a bit more in line with your interests, because these muddy beds do not behave like sandy beaches. But before that, one of the things that also turned out to be quite important was that it would be really handy if you can keep at least one hand clean during these kind of field work. It's not always possible, but to use instruments like the GPS or other things, it's really helpful to keep at least one hand clean. That's one of the rules of geo. Let's continue. Erosion. So we did some measurements on tidal flats in the Western Scheldt as well. This is one of the first measurements that we did with this instrument again, where we measured the flow velocities, waves, but also the bed level change. And what you see here is actually a similar pattern as what we saw before. The blue line is a part of the tidal flat where we see the bed level changing, and especially here we see there's a substantial decrease of the bed level. And that is the period, again, where we have a small water depth for a long time, but also quite high shear stresses because of the higher waves and also because of the higher flow velocities. Again, the red line was too high, so it didn't catch the wave, the storm. But zooming into this blue line, we see the change in bed level, and you see that we captured quite some points of the erosion, and we identified this gray box as the erosion period, and that also kind of marks the threshold for erosion. So we indicated that in this case, approximately, what is it, 0.2 Pascal. We see that from here on the erosion starts and it stopped approximately here again. So with this, we could get an indication of the critical shear stress. Without doing, for example, gust chamber experiments. So only by using this ADV, where we measure the bed shear stresses as well as the changes in bed level. The next thing what we did, because we can determine that for this period, but of course we can also determine it for this period, etc. And if we then plot these different critical shear stresses, we get something like that. Depending on the original bed level, we see that the critical shear stress is increasing if we go deeper into the bed. And that's of course not that strange, because the deeper you go, the stronger the bed becomes and the more difficult it will be to erode the material. So if this is the erosion rate, so this is the Parteniades equation, we see that the critical shear stress here is important for determining whether there's erosion or not. And the deeper we go, the larger this critical shear stress will be, and therefore the smaller the erosion rate will be. We also tried to get a value for the M coefficient, or as over here, the erosion coefficient. There we did not see such a very clear relation. Well, this is on log scale, already indicating that there's a widespread, but it's closer to a constant value than that there's a strong dependence of the depth. Maybe only some changes over here. Talking about the bed strength development, I think that's an intriguing part also because, let's say, if we look at numerical models, most of our numerical models have an erosion formulation like this in it, with a uniform and constant M and a uniform and constant tau critical. Well, we already showed here that this tau critical is not uniform, and it's also changing over the depth and thereby also changing in time. The question, of course, is how can that develop? And this is another longer term measurement in the Wadden Sea. The mean flow, or sorry, the mean wind speed is indicated over here, or the wind speed, and this is the bed level in blue. And what we see is that it is changing a little bit, but here on the right hand side is the shear stress. We see that there's a storm over here, and the bed level drops and to a certain level because of the let's say storm 1. We directly see that storm 2, which is also relatively high wind speed and also relatively high shear stress, there's almost no response. So apparently the critical shear stress is already increased so much by this drop that no erosion takes place anymore. Well, then we have another period where the wind is from the northeast and we get accumulation of sediment, so the bed level increases again, until we have a relatively, well, it's not indicated here even, a relatively small storm where we directly erode the material again. So here we build up the sediment with kind of fresh material, increasing the bed level, but there's no real strength development, I think. And with even a very small bed shear stress, we already eroded. And interesting enough, it erodes approximately to the level reached at the first storm. So this line is an indication of that. So it's again going to the point to the bed level where we were just after the first storm. And here we get another slight increase. This is somewhat worrying for our models because this would imply that we have to account for all kind of non-uniform critical shear stresses and possibly also erosion rates. So the strength of the bed increases if we go deeper into the bed, limiting erosion. So erosion is not just not just depending on the shear stress, but highly depending on the history as well. Time is needed to develop this strength, and yeah, I think we need some better insights in that. And Roy van Weerdenburg, he's a PhD doing research on this. He's looking in this kind of things and among others measuring what is happening in this top layer. Finally, what's the fate of the tidal flats, and can we do something against it? But again, another advice. One of the things that we did is organize our laboratory, and that also really helped I don't know how your laboratories look like, but this is a picture that we took just after we cleaned everything up. And as you can see, we now have boxes with images, etc., so that you can see what's in it, etc. Our technicians really made a big difference there. If we compare this to the period when we started, I think that's a big difference. And very important, do as much as you can do at the laboratory instead of doing it in the field. In our early phase, we did a lot of building of the frames on the tidal flat. That takes a lot of time, and it's annoying, and you can do not as much as you can do if you prepare it super well. But again, what is the fate of the tidal flat, and can we do something about it? As indicated, the eastern scald. Looking at this part, there's a storm surge barrier over here and over here. Here's a picture of that, and it reduces substantially the cross section. So the tidal range is decreasing, and as a consequence, if we sum up all the tidal flats and determine the mean bed level of that, and plot that over time, and Lodewijk de Vet did that, then we see this kind of decline. And this decline is a first almost linear relation, but at a certain moment the rate reduces, and this reduces partly caused by the fact that the lowering of the tidal flat also increases the tidal volume, and that has impact again on the infilling of the tidal channel. So there's a little bit of a feedback, but still, as you can see, we still are the tidal flats are still lowering, and that's quite a concern because we have to mitigate that because of European laws. So how do we do that? One of the things is nourishments. So we nourish the tidal flats, bringing sand onto the tidal flats by dredgers, but also redistributing it by these bulldozers, as you can see over here. A very clear and logical thing to do, in the sense if you want to increase the bed level. Other possibilities are oyster reefs. These are artificial oyster reefs in the sense that it are real oysters, but they are put there on gabions, and at a certain moment it grows into a natural reef, as you can see over here and as well as over here. Unfortunately, one of the reefs was a bit too high, and then you see that the reefs do not survive. So that's another lesson. Also, talking off with all the ecologists, because they can also tell you when and where oyster reefs, oysters survive. And actually, these two reefs are quite close to each other, indicating that it is not very straightforward what the exact height of the reef should be. If you put it too high, then it's dying. But on the other hand, if you put it too low, then it's less effective. So it's a bit a tricky thing. Other methods, this is in the Western Scheldt, we see that there's a lot of these groins are built to reduce waves and also reduce the longshore velocity. And in that sense, we reduce or at least we kind of keep up with the intertidal flats. Let me see where I'm now. Sorry, I saw that there's a chat. Oh yeah, no. So tidal flats are at risk of drowning at the moment. Also in the north, in the Wadden Sea, local mitigation measures are taken, one more effective than the other. one big question is still what's the impact of on the larger scale? We can do that locally, but is there an impact on Estuarine scale? I'd like to round off. There's much more data to come. We started a new project called Delta Enigma, where we measure in rivers, estuaries, and also coastal seas for 10 years. I'm looking forward to that, and we will deploy much more instruments as indicated. We're also happy to have researchers from abroad. So if you're interested, let me know. And finally, every 2 years there's the conference Interco, and this year or in 2026 it will be in New Orleans in September. Gerald Smith from the Army Corps is organizing it together with Carl Strom and Courtney Harris. And last time we organized a summer school in Incheon, that's in Seoul in Korea. And as you can see here, we were with a group of PhDs and lecturers on tidal flats, almost in the middle of Seoul, where you can see these kind of buildings and tidal flats. So they integrated the urbanization in the tidal flats as well. There's no announcement yet, but it will be on the 7th till 11th. But keep an eye on intergo.org. And finally, thank you very much, and a lot of thanks to all the people below. Thank you very much, and I'm looking forward to hear any questions.
Great. Thank you so much, Bram. What a great lecture.
Thanks.
So with that, I open it up for questions. So as usual, please raise your hand, and then I will call upon you or put your question in the chat and I'll read it out for you. I already see one hand up. This is Jandash. Jandash, please go ahead with your question.
Hello, thank you for the presentation. I really enjoyed it. My question is about the bed strength. In the plots that you showed, the bed strength was in the order of pascals, and it was changing like with, let's say, points of pascals, like 0.5 pascal, 0.2 pascals. I was wondering, like, how did you like accurately measure these orders, and like which tools are you used in order to capture these changes?
Yeah, we do it indirectly. So we determine the flow velocities and the wave characteristics, and based on that, we determine a bed shear stress.
Okay.
And if we have a time series of the bed shear stress, and we look when the bed is eroding. So when the erosion starts, and then check, okay, if the erosion starts, at that moment we think that the threshold is surpassed, let's say, and that is then the definition of the bed shear stress.
Okay.
And in our case, it's like in the order of 0.2, 0.3 Pascal, something like that. And yeah, other ways would be with a gust chamber, Aeromes, or those kind of instruments. But it's always always be careful in how you exactly define it, the bed shear stress. But so we don't have a direct instrument. I think there are instruments to do other kind of things, but yeah, possibly Nina knows these kind of things better than I do. We tried some veins and other things, but we were not successful in combining that with the flow velocities.
Yeah, I'm familiar with the vein shear test that you mentioned, and getting this precision from a vein shear strength test might be tricky. That's what I was asking the first section. Thank you.
Great, thank you. The next question is coming from Joey. Joey, go ahead.
Well, yeah. First of all, thank you, Bram, for a very interesting lectures. Actually, the question previously was also mine, because for us geotechs, right, for fluids, we think, there's no shear strength. You talk about a Pascal, we'll talk about kilopascals to begin with, for soft mud. But the tips that you pointed out as working in a muddy area like the sled. I think that's really interesting there. We do have some big sleds over here for sledding in Alaska. So I think I'm going to bring one of those, maybe, get some of news to the site just in case. I was also curious, because you have so many little muds, in the Netherlands. Was there, many accidents reported in the summertime when people visited those sites? Because what we are interested here is the trafficability, right? I was
Yeah,
just curious.
yeah. So going onto the flats is only possible with the guide. So there are no people going on the tidal flats without a guide, I think. So I'm not aware of any casualties or something like that. It's pretty organized actually, these kind of
Okay.
things. So yeah, well, it's also something I didn't mention, also because I think that's known, of course, for our field work. Safety first. So we always go with at least 2 people on a tidal flat. And yeah, we never go alone. Also because, well, in the Western scale, the water level can get a couple of meters higher than the bed level. So you can drown in principle, but on the other hand, we are often very close to a dike. We're not so far. We did some field work in China as well, and that was more extensive flats, and there we had to be even more careful. But also there, if you are with more people, and yeah, the wetsuits really helped. That was a game changer.
That's a good point here. Yeah, I just wish people here are so disciplined, not to venture into those areas by themselves. Yeah, we once in a while we have accidents. People get stuck, people get drowned. Here in Alaska. But yeah, I'm glad to hear. There was not much reported here. Thank
Yeah.
you.
Thanks.
Sophia, I have you next.
Hi, Bram. Thank you so much. That was a really great lecture. I was wondering if you could comment a little bit about how you juggle kind of getting high quality dense measurements in a certain space and like covering a large spatial area with measurements. Like, how do you pick your locations? What's more important to you? Can you just give a little bit of insight into that?
Yeah, it's always difficult because on the one hand, you want them close enough so that you have, well, let's say cross section. But so we often stay on a single tidal flat, let's say one of the fringing flats, and then if we have more instruments, multiple cross sections. But we also indeed now and then go to kind of hop to another tidal flat. I would. We always had like 3 or 4 instruments or frames at least on a tidal flat, so that because otherwise it's difficult to see changes. Like I showed this sudden bed level changes. If we only had the upper tidal flat, we would not have seen it. And also explaining what you see at a certain location is easier if there's another instrument kind of close by. Yeah, I think in that sense, the main advice is make sure that you have enough instruments. And that's of course an easy answer. But what we did, especially in the beginning phase, then we only had 1 or 2 instruments, but we teamed up with quite some other people, other institutes, to make sure that we had multiple instruments, and from that we kind of grew. Now we have a lot of instruments, and we actually do the same. So if there are other groups, especially of course in the Netherlands, because that's an easier thing to do, if people are coming, they can use our instruments for free. The only thing we require is that we get a working instrument back. So we don't get the value of the instrument. So if an ADCP breaks, then they either have to repair it or buy a new one. but not, let's say, the value of an ADCP, because that's that's not as high as it is for us, let's say. And yeah, most of the time that worked. So up till now, we did not lose instruments actually.
Thank you.
Great. Do we have other questions? Well, people are thinking, I have actually one. So one thing we are seeing here a lot is that we see differences in sand versus fines content. So we see some tidal flats that are literally transitioning from one zone to the other, and we see others whereas more spatially the one flat is sandier, the other one is really muddy. Can you comment on that, how that is in the Netherlands flats?
Yeah, we see that too. And I think we had a PhD some time ago already, Matthijs van Ledde, and he looked in the Wadden Sea, and there's a strong separation. Either we have the more sandy, or we have the muddy flats. And there's almost nothing in between.
Oh.
And what the exact reason is, yeah. It depends a bit. Like is there enough sediment available? And also, can the sediment stay, especially the fine sediment? So most of the time we see that the sandy parts are a bit more in the middle of the estuary, for example, in the Western Scheldt and also Wadden Sea, while the fringing tidal flats are mostly muddy.
Got it. Great, thank you. Emily, go ahead.
There we go. Okay. That was a great talk. Thank you very much. I was curious, you showed a nice frame with your Nortec ADVs to get the highly resolved velocity and turbulence and bed elevation. How was it mounting that frame? Did you have success with that? Was it challenging to make it immobile?
So what we do is we have these aluminium pipes that you have for scaffoldings, and they have these connectors too. But we made ourselves these connectors. So a kind of a connector that you already put on the ADV so that you can easily connect it to the frame. I think those are the things. I'm not sure if I let me see if I can show the example.
So like a vibration damping clamp to fasten to a frame.
Well, we don't call it vibration damping in the sense. Let me see if I have because we changed our the design quite a lot over time. I'm not sure. I think I have the. Wait a second. No, I cannot, because the ones that I actually showed were older ones where we still have a wooden plate. But at the moment, I can, if needed, also send a picture later on. But what was useful for us is to put already everything as much as possible on the frame, or sorry, on the ADV, so that the only thing you needed to do on the tidal flat was hammering two vertical poles and then directly hang the horizontal bar with the ADVs, etc. in it.
How did you mount it? How did you mount the foundation in the tidal flat? How deeply did you have to bury that?
We do it like 1.5 meter, 1 meter, depends a bit.
Wow. Okay, thank you.
But most of the time we can just push it downwards.
Okay.
We have this hammer, like a sledgehammer, a bigger hammer, but also this thing that you can, if you have poles in your garden. Well, I don't have a garden in that sense, but I can imagine that people do that in their gardens.
Excellent, great.
Yeah, and the cool thing is that if you leave it for a longer time, then everything gets stiffer and sturdier. So the frame is getting better after a few weeks.
Great. Thanks, everyone. In case you have further questions, I'm sure you can contact Bram via email and get some more answers. Again, thank you so much for this lecture, Bram. We really appreciate it. I hope we can stay in touch with you and continue sharing results and ideas. That would be greatly appreciated. And again, thanks. Yeah, so Bram's email is actually in the chat right now. I also want to, in case you haven't seen the chat, people really enjoyed also your lessons learned. I did that.
Oh, okay.
I think that's great. So thanks again for the great lecture. Thanks everyone for joining. And so in the next month, we have Barrett Kurlick from Dalhousie University joining us. He actually in person at UF to deliver the Tidal Flat seminar. But for those of you who will not be here in Florida, we will, of course, broadcast it via Zoom again. Sherilyn, do you have the date for that? I don't have it in my mind.
December 11th.
December 11th. So put that already on your calendar, everyone, if you're interested in joining. Thanks again, Bram. Thanks everyone for joining. This was fantastic. And I hope I see everyone at the very latest in a couple of weeks. Thank you.
Thank you.
Thank you, guys. Bye.
Thanks, Bram.